ATSA the orbit instructions. If the group action is okay, so let's start. Not to waste time. Just now, will also ask me a question. Ask a question. On this proof here. Okay, that's about this part A. So you given a group, okay, and then you consider a subgroup of the group. Once you get a subgroup, what can you do? You can form a coset, okay, and then the coset of H will partition the group, and then this induce a natural action of the group on the set of coset, okay, because group elements will permute the set of coset, okay, permutes. Does it make sense? Okay, so when I talk about these, right, you should create an image in your mind. What is the image you need to create? Okay, you have a group, right? And then within the group, you have a subgroup. Okay, with this subgroup, you can form cosets. Okay, you can form coset, which partition the group. Okay, so you should imagine a subgroup as a knife, right? You can use a knife to cut a cake. Okay, for example, group is a cake. Then you can take any element in your G, okay, and then add, multiply with your coset. Okay. Okay. Sorry, let me put X, G in G. Okay, you can do this action here. Okay, what's this action? Okay, what's this action here? You simply multiply with your representative. Okay, and get the corresponding coset. Okay. And then this will permute the set of coset. And then I want you to show that the action is transitive. What does it mean by transitive? The group action is transitive if the orbit of orbit of orbit of what? Yeah. So let's write down action is transitive. Transitive if orbit of S is S. Okay. So this S is in the S. Okay or not? Actually, this is for OS, right? If your set can only partition by OS. Okay. So why there's another partition here? Why there's another partition? Because OS form a equivalence class. Okay. No. The orbit of S in S forms equivalent classes. Okay. So you can slice your G with H. You can slice your S. Okay. So this is a group. You can slice your set with or S as well. For example, like this. Or S1 or S2 or S3 or S4, for example. Okay. Okay. It is true for all x because what is orbit? Remember what is orbit? So you remember how the Earth is orbiting around the Sun. Okay. Orbit means all the path, okay, all the place that the Earth can go to, all the element in the set can move using group. Okay, you use group element to move the object. Okay, and then you collect all these possible places that the set element can go to. This is called a orbit. Okay. So to show that a group action is transitive, you need to show that orbit of any element, okay, is equal to the whole set. And that's means I want to show that O of something is G of H, G over H. So this what things can we pick? We can easily pick H. Okay, we just pick H, right? We just pick H. So meaning if I pick H, okay, I need to show that I can go to the other coset. Okay, I can move to the other coset by just acting by the group element. Okay. Is it true that I can get from H to the other coset or not? From this picture here. Is it true? From this picture here, okay, can I get from H to other coset or the other coset? Can or not? How? I just multiply my H by C, B, and A. Then I can reach all the coset. So these all coset are in the same orbit. Okay or not? Does it make sense? Does it make sense? If don't make sense, it's okay. You have to ask question, okay? Because I don't know what you are thinking. Okay or not? Any question? Yeah, so I mean, if you don't 如果你不知道不会，不是我希望你听，OK，因为你不听，你又不会，我是帮不了你，OK 吗？Does it make sense? If you don't understand, please listen. If you don't listen, I can't help you. Okay 吗？Okay. Okay, let's recap what we have from last time. And let's pick up from what we stopped, where we stopped last time. So last time we talked about if I have a group action, there is a correspondence between group action and the permutation representation. Okay, so I have a group action here. And then I can define a homomorphism, okay, from a group to a permutation of a set, okay, a set. So here S is a set. So G, a group, and S, a set. Okay, so in the group action, what's the difference between these two? Group action, we only know a map from G cross X to X. Okay, but on the right hand side here, we have a homomorphism. Homomorphism means what? The core domain and the domain have some structure. Okay, we have homomorphism between groups. Okay, what are these two groups here? So these are G is a group, okay, and permutation of S is a group. Okay, so this is a like S of S. Okay, so you permute the element in S. Okay, so one of them is the symmetric group, one of them is the set we are playing around. Okay, we are permuting element in the set. Okay, how does this work? Still remember or not? How does this work? Huh? So you have a group action on X. What does this mean? This means that you have a map between, I give you any G, okay, I give you any S, you produce me another S, okay, which is just GS. Okay, you produce me another X. Okay, in other words, what? In other words, what? Where's the mapping? Yes, this is the mapping, correct? Then here is a map. Okay, this is the map, correct? From a product set to a set. Okay, this is a map, correct? So you need to tell me how they compose. Okay, if you're gonna tell me this map, how they compose here. Okay, how they compose here is important. You need to tell me. Okay, define this. Okay, you need to tell me this. All right, is it okay? Okay. Okay. So in other what? In other word, what? In other words, if you just look at a single element G, okay, and then you look at how it add on all the element X, you can see that X gets sent to GX. Okay, so this is how we go from group action to the permutation representation. Why? Because in the permutation representation says what? Give me a G, element G. You need to tell me how it permutes with the set element. Okay. So you need to give me a G. Okay. Tell me how this G commutes the element in X. Okay, no. This is a different way to see the group action. Okay. So meaning a group action is equivalent to give a permutation representation. If my set has more structure, right? For example, my set is a vector space. Okay, what's the invertible operation on vector space? As a finite dimensional vector space. So the vector space is finite, has finitely many bases. What can you do? Try and link to your what have you learned, okay? Try link to what have you learned. So if X equals to V, a vector space with dimension of V is less than infinity. What is it? What is the perm of S? What's the permutation of vector space mean? What's the invertible? Uh, what's the invertible element in the vector space? Hmm? Any idea? What's the map between dimensional vector space? Okay, this is the thing you have to know first. What's the map between finite dimensional vector space? Is there any specific form you can write down? So let me write down. So what is map between, what is a map between, for example, iron to iron? Maybe we can be more specific a bit. So what is a linear map from iron to iron? You know about anything about linear map between iron? Sorry? Yeah, linear map. Sorry? Linear transformation, yeah, linear transformation. So linear transformation between iron, what do you have to tell? You have to tell about how you send the basis. And these will determine everything where the vectors get sent to. So meaning what? P can be represented by a matrix. Okay. You can use matrix to write down the linear map. Okay or not? Okay. So if it is iron to iron, this matrix size is just n to n. Okay. Does it make sense? Okay. So invertible matrix means what? What are the invertible matrix? Determinant not equal to 0, so what's the set called? GLN. Okay, so these are the general linear group. Okay, so if V is a vector space, then phi from G to perm S is just equals to GL and GRN of Rn, where n is equals to dimension of V. Okay, and then this is what we call the representation theory. Okay, so representation theory studies groups in terms of matrices. Okay, so this is what called the representation theory. And so this gives a representation. Okay, so I give you a representation, you can give me a group action. You give me a group action, we can study the representation. Okay, does it make sense? Okay or no? Yeah. Okay. So this representation, right? Sorry, representation. Okay, actually grew up from chemists. Okay, Frobenius. Okay, Frobenius, a chemist. They study the experimental data. Okay, and then see how this experiment data change. Okay, by changing the variable, right? Experimental variable. Okay. And then this data form a vector space. Okay, and then they somehow can invert their chemical process, for example. Right. Okay. So representation theory really grow from experimental process. Okay. And what have we covered last time? So we covered last time what's representation to be faithful. Okay. And then we say that the group action G on X, okay, is faithful if the corresponding permutation representation G to perm S is injective. Is injective. Okay. So what does this mean? Okay. So you need to consider a group element. Okay. get sent to the MG. What's the kernel of permutation representation here? What's the kernel here? Identity. Okay, so it is the identity that fixes. Let me put some up here. So what is the identity in perm X? Okay, so what's the identity in permutation of X? It is the identity map, okay, that fixes all the element in X. Okay, so this is the identity. So who fixed this? All of this, okay? It could be everything, right? Okay, so for example, let's say I define a group action G to G. So let me define a group action on a group in a set X. Okay, how do I define this set here? I just define by G compose S equals to S. So meaning what? For every group, they do nothing on my set. Okay, so this is what we call a trivial group action. Okay, so everything acts like an identity. If I have rotation on my object, I say this rotation, don't move my object. This reflection, don't move my object. Identity also don't move my object. I can do that because this composition is what I define here. I can change. Okay, I can change how I add on the set. Okay, if I do this, this means what? Identity fix the object. Rotation fix the object. Reflection also fix the object. Okay, this depend on how I define. Okay, so group action depend on how we define the action on the set X. Okay, then what? Then this phi here, the kernel of the phi here is the whole set. Okay, because I say that everything in my group act trivially. So kernel of the permutation representation is everything. Does it make sense? Okay. Any question about this? Is the whole G a stabilizer? Is the whole G a stabilizer? So when you talk about stabilizer, you need to talk about stabilizer of an element X, right? Okay. Then let's say we pick one element in X. What is the stabilizer of X? And then in this case here, yes, the stabilizer of every X is in fact the whole group G. Right. Stabilizer need to be a subgroup of G. Okay, in this case, is the whole G. So this is called a trivial group action or trivial representation. So this is not very interesting because you can't really see how the group elements are different with each other. Okay, so if we want to study how to discern between group elements, it is better that we get a faithful representation. Okay, faithful representation means what? The homomorphism here is injective, meaning what? What does it mean by homomorphism here is injective? What is injective? One to one. Yeah, so what's one to one? If FA equals to FB, means A has to be equal to B. Contrapositive is what? If A not equals to B, then FA is not equals to FB. Okay, so meaning you have two, if it is injective, meaning if you have two different group elements, okay, you go and add on the set, it will give you two different objects. Make sense or not? So how you study whether these two group elements is the same or not? You go and add on the object X, the set X. Right? If the group elements are different, then it will produce a different action on the set X. Okay or not? Does that make sense? Okay. Yeah. Okay. Yeah, so what? So I posted up my work on the Moodle if you want to have a look. It's about the faithfulness of a break group, a generalized break group, which we call a type B break group. And then it's a generalization again on the break group. So it's called a two break group. Yeah. And it add on an object called modules. Okay, I'm not sure our class have time to go to modules or not, because we have 5 weeks on rings. Yeah, I'm not sure we can have time on the modules, but we'll see. Yeah, module is a generalization of vector space. A2. A2 will do Galois theory. Yeah. Yeah, of course we will deal with module, but yeah, sure. Okay. Okay, any question about this group action, faithfulness stuff? So I have put out the assignment 4 already. So there are 5 questions. If you download before today, you only see 4 questions, but there are 5 now. Okay, please download the latest. Tomorrow 6. No. Don't be worried. Okay. Yeah. Don't be worried. I just forgot to type that question. Yeah, I just forgot to type the question. I have the question in my mind, but I forgot to type it down. Then this morning, when I wake up. That's only you wake up. No. Not like this, not like this. Doesn't work like this, okay? Not everything that you predict can happen. That's what I want to say. Because in your class, this is the problem. Of course, this is also my problem. Actually, this is most a mathematician problem. Because we like to predict stuff, right? Because you like mathematics because you think that it is predictable. Right? Because I compute this, next question, change a bit, should get the same answer. You like to predict stuff. Okay? Actually, this is not bad, but don't make this how to say? Don't make this a problem to you. That's what I would say. This is not bad, but I don't want you to make this a problem to you. It become a problem that haunts you. You get what I mean? Yeah, don't make this a problem to you. This is a skill. I mean, skill it's like a knife. It's like a knife. Knife you can use to cut stuff. You can use to hurt stuff. You can hurt yourself. You get what I mean? Okay or not? Yeah. Okay. All right. Yeah. So only 5 questions. Okay, only 5 questions. Don't be worried. I won't add more questions. Okay. You can only believe me. So this is the setting here. You can only believe me because this is my class, right? So you can only believe me. So there's something that you can change, something that you cannot change. Okay. Yeah. But anyway, yeah, just follow your heart. We will deal with it. Let's see how we deal with it. So the interesting about this word is things will happen no matter how. It's the way you deal with it is the difference. Okay or not? In this world, the problem is the same, but how you deal with it is different. Okay, so this is the part here. See, you missed the most interesting part. Representation. Okay, yeah. Okay or not? Hey, where's Mingxiu? Does Mingxiu disappear? Is he okay or not? I think for the AA. Yeah. How is he? Is he okay or not? Don't know. Yeah. I don't know why he had to get help. Huh? Sorry? 瞧一瞧他。好像是你来的时候带上他了，他每次都迟到。下次你来的时候带上他。Yeah，太厉害。Okay, let's finish up the last part on the group action. So we have looked at a specific group action on COSET. Now we will look at a special action on G. Okay. So let's consider a specific action G on itself. Okay, G acting on G. Okay. So we can use group multiplication to do that, but that one will be the just normal regular representation. So what we'll do here is using conjugation. Okay, this is called the conjugation. Sorry, this action is similar to IOC, LOC. It's not right because we don't just look at G multiply with X. We multiply X by G in the front and G inverse at the back. Okay, but how they multiply is using LOC. Yeah, how they multiply together is using LOC. Yeah, but we put G in the front, G inverse at the back. This is what we call a conjugation. Again, we conjugate. Is it easy to see that this thing is in G again? Because everything here is in G. G is in G, so G inverse is also in G because it's a group. Then composition of G elements is still a G element. Okay, so you could check. Okay, you can check whether a conjugation satisfies the group action axiom. Okay. Okay, so you need to check the 2 point there. Okay, does E sense every S to S or not? E inverse is what? Is S again. Okay, and then does it satisfy the associative property or not? Okay. So let me write down the associative part. So for the associative part, you need to check what? You need to check that, for example, G1, G2, X on G1, G2 inverse is equals to is equals to what? Is equals to everything. So let's check. Let's check this. Okay. So let me write down here. Check that G1, G2 on X is equals to G1 on G2X. Then that is what? That is just G1, G2X, G2 inverse on G1 inverse. Okay, you just need to check this. And you can see that this is true by associative. Okay. Can you see here or not? If I put G1, G2 here, but G2 is the one that closer to X. This means what? This means the order is like going from the right to left. Okay, this is what we call a left action. Okay, if we define a right action, it will be the other way around. Okay, no? So really, if you want to keep your order right, okay, how you compose with X, you could write this as G2, G1 on X equals to G2, G1X. Then this one will be following the way you compose. Okay, this will follow the way. This is what we call a left action. Okay, left action. What have we been studying is just a left action. We can do right action as well. All right. So since we have this action, right? Okay. Since we have this action, we can define orbit and stabilizer again. Okay. So what's the stabilizer of an element here? Can anyone think of what is the stabilizer of this group action? What are the elements that stabilize the object? Sorry? Sorry? Fix? Fix what? Can you be louder? Yeah, just fix it. But this is a special action, right? Okay, what does it mean by this action fixes something? So let me write down. So this group action is fixes x means what? Gx G inverse equals to x, right? Okay, so what's this actually? What are these? Gx equals to Sg. What's this? Sorry? Commutator. Commutator. This is not what we call the commutator. This is the property of a center. Okay, so this is what we call a centralizer. Centralizer of x. Okay, so it is denoted by zs. Okay, so a fixed x, okay, you can consider the centralizer. Okay, centralizer. So meaning what? This centralizer here must contain the center, because center commute with everyone. In particular, it commute with x. Okay, so this, so okay, remark here. So the center z of G contain is contained is contained in ZC ZX. So this ZS here is much bigger than the center. Okay, no? Because center commute with everything, but this ZX here just commute with X. It could be greater than the center. Make sense? Okay. So centralizer is like make X central. Okay, next. The orbit of this action is very important. Okay, it's very important in pure maths. So the orbit, so it's all the places that you can go in your set, in your group by conjugation. This is called the conjugacy class. Okay, this is very important in pure maths. Okay, conjugacy class of X. Okay, so sometimes or in your textbook, it will be denoted by Cx. C is the conjugacy. Cx equals to x prime in G. X prime equals to Gx, G inverse, for some G. Okay. So you take an X, you conjugate with all the elements in your G, and then collect all these elements. Okay, this form an orbit, and then this is what we call the conjugate C classes. Okay. So for example, in your what? In your linear algebra, right? Okay. So how is B similar to a diagonal matrix? If there exists a P such that P, sorry, what's the notation you use? A equals to PDP inverse, right? So if you take the D element, a D diagonal matrix, you conjugate with any P inverse, all these A will be living in the same conjugacy classes. So meaning what? So matrix with the same eigen values belongs to the same conjugacy classes. Okay, now. So let me write down here. So example, matrices with same eigen, same set of eigenvalues live in the same conjugacy. Okay. Okay. So proposition, we have the order of group is the order of centralizer times the order of conjugacy classes. Okay. So this what's this? This is the counting formula. So counting formula, what does counting formula tells you? It tells you that the order of the group is the order of the stabilizer times the order of the orbit. Okay. And how you get this counting formula? This is obtained from the orbit stabilizer theorem. Okay. Stabilizer form a subgroup. So definitely ZS will divide G. Okay. So but what's the coset? What's the coset of the stabilizer? Okay. By the orbit stabilizer theorems, it tells you that the coset of the stabilizer is what? Is the orbit. Okay, it's the orbit. Okay, so that's why we have this counting formula here. Okay, next. So this is just a specific case. Okay, how we apply the counting formula, because we have fixed our group action as a conjugation. Previously, those are general group action. Next, we know that the centralizer, okay, of Zx of an element x of G, okay, what does it need to be satisfied? It must contain x itself. Okay, why? X inverse is what? It's just x. So meaning x fixes itself. Okay, no? So maybe I just quickly put some thinking here. X inverse is just x. Okay, so x fixes itself. Okay. And then, like what I said just now, this centralizer must contain the center. Okay. So you need to show that for every element in the center, it fixes x. Okay, it fixes x. Can you think that why is this obvious or not? Can you think that why is this obvious? So for every element, so you take an element y in Z. What does this y have to satisfy? Yx equals to xy for all x in G. Okay. But in the centralizer, we only look at a particular x. So meaning the center will commute with my x always. Okay, so it is in the centralizer. Does it make sense? Yeah. Okay. Okay or not? Okay. And then B, what do we have? For all x in G, okay, if G is in the if x is in the center, what does it mean? This means that my x have to commute with everything, right? Okay, this means what? The centralizer of x is the whole G. Okay, but by this counting formula here, if I know the centralizer is the whole G, what is the number of my centralizer here? A, so order of G, so C, so let me write here. If, okay, so let me draw here. If the order of the centralizer is G, okay, what should be the order of, did I say something weird? What is that? Yeah. So if the order of the centralizer is the order of G, okay, what should the order of my conjugacy classes be? 1. Okay, it's 1. Okay, meaning what? What is the single element inside CX? It is just X itself. Okay. So this is the if and only if statement here. You can try and prove it, but you can lay out every definition, and it is kind of trivial or obvious. You can do it. Okay, you can try it out. Is it okay? If not, we can briefly discuss here also. But the problem is you need to write down. Okay, try write down. Okay or not? Okay. Yeah. How's the proof go is just how I discussed just now. Definition again. So there's a thing we call the class equation of a finite group. Okay. G is the order of G is equals to the sum of the conjugacy classes. Okay. Because conjugacy classes are the orbit partition the group. So you can add up all the order of my group. So there's some remark here. So let's look at the C1. What's the centralizer of what's the conjugacy classes? Sorry, what's the conjugacy classes of identity element? It's just the identity itself, right? You take all the G, E, G inverse, you always get E. Okay, so this is the orbit of the identity. So there's only one element here, okay? Namely 1G. So what? So the numbers. So we have some restriction on this equation here. So the number on the right-hand side of the class equation, we know that the order of the centralizer must divide the order of the group. Okay, from the counting formula just now. And one of them must be, at least one of them must be equals to 1. Okay, at least one of them is 1. Is equal to 1. Okay. Okay or not? Okay. So let's look at one example here. Okay, let's look at one example. What is the class equation of S3? Okay, let's work out this example here. What's the class equation of S3? Okay, what's the class equation of S3? So what S3 we want to use? Let's use the presentation by generators and relation. Okay, let's write down the free group with relation. Because I don't want to compute the function composing. Okay, I just want to remember how they are composed together. Okay, I don't want to go into checking functions. Okay, I just want to see how they compose. So the order of S3 is 6. Okay, so what's the don't try and work out what are these? What are the conjugacy classes of these? I give you 3 minutes. See if you can work anything out. So you need to take all the element here. So 6 element there. You need to conjugate them with the 3 elements here. Okay, so what are the 6 elements? Let's write it down. You have identity, x, x squared, y, and then what? And then yx, and then yx. Okay, so use this 6 element and then try and conjugate with e, conjugate with x, conjugate with y. What do you get? Let's give you an example here. Let's give you an example. So C on E is what? So you need to take E with E inverse, X, E. What's the inverse of X in this case? Is X squared. X squared equals to what? Okay, and then X squared E, X squared inverse equals to what? Right. And then so on. Okay. Sorry? Yeah, for E, you only get E. Okay. But how about the rest? How about X and Y? Can you try out? You know what to do? Can try? Yeah, try. Yeah, try and compute. What's the conjugacy classes for X and Y? Yeah, try and write down. Please write it down. Don't just think. Write it down so that you will remember. Okay. Try and compute. What is the conjugacy classes of X and Y? Yeah, try and write it down. Write down. Okay, what's the conjugate sequences? Let me get someone. Um, Ryan, can you compute what is CY and then let us know what is CY later? And then get someone. How about Michelle? Michelle, compute what is CX and then let us know later. Okay. So finish. Got it, Michelle? Finish? Try, just try, just try. What's the conjugacy classes? Sen, x squared. Do you have identity or not? Huh? You should have identity, right? Okay. How about cy? Sorry. Why do you got identity? Okay, so this is a good question. Why do you have identity? Anything conjugate to identity or not? Identity commute with everyone. And so, I mean, so who conjugate with X that you get identity? Do you have identity? No, don't have. Don't have.
I think the first three is X and then the last three is X, correct?
So what's this extra thing here? This X square finish or not? Is it finished? Okay, let me. So, okay. So should there be an identity here? No. Why? Why? Otherwise, this orbit doesn't partition the set. Okay. So the question is, are there any other element here? No. Okay, let's keep like this first. Okay, what's y? Conjugacy cluster of y, yeah. Y, x. Y square. Okay. Okay. Everyone go the same calculation or no? Same calculation. Does everyone go the same calculation? Got the same? Got the same? Same calculation? If not, we can check if you want. Check together. Everyone got the same calculation? Okay. So this, you see, there's 6 elements here, right? Okay, there are 6 elements here. But these 6 elements are coming from the element of group. Okay, they live in different set. So this means what? This orbit partition our group. Okay. And then the class equation here is what? 6 equals to 1 plus 2 plus 3. And then 1, 2, 3 here all divide 6. Okay, such that 1, 2, 3 all divide 6. Okay. And then there's a number 1 inside there. Okay. So this is a class equation belongs to 6. Okay. Yeah. Yeah. Any problem? 6 equals to 1 plus 2 plus 3. That makes sense? Okay. But in the group level here, this is the what happened. Okay, so this is what happened in the group level. Okay. Any question before we leave group? Yeah, we'll leave groups. Yep. What do you mean? Partition stronger than this? Stronger than what? What do you mean? Mm-hmm. Uh-huh. Why do I need this? So this will tells you the number of different conjugacy classes. So how do I say? Because remember how you get this conjugacy classes, you need to conjugate with all the element in G, right? So let's say my G is very big. Do you want to conjugate with all the elements to see how the conjugacy classes? Right. So you can use this formula here to somehow restrict the order of my conjugacy classes. You can guess how big is my conjugacy classes. Yeah. Yeah. I mean, yeah. Yeah. Is this what you want to ask? Or yeah. What's the use of this class equation, right? So you can roughly know how big is my conjugacy classes. What kind of number can appear in a conjugacy classes? Okay. Hmm. Any other question? Yes. Sorry. Compute CX. Just check for sanity check. So let's check what is CX. So let's do a sanity check here. If CX wrong, CY have to recompute. But let's check. So we have identity X. What are these? X squared, Y, then X, Y, X, and Y, X squared. Okay. And then we know that X cubed to identity, Y squared to identity, and then YX equals to X squared Y. Okay. And then we want to compute, we want to conjugate this with X. So we conjugate with X. X, 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 and then take the inverse. Okay. And then we see what we get. Yeah. So first we get X. Second, we get X. Third, we get X squared, X, X, X to the minus 2. What is this? This is again X. What is Y, X, Y inverse here? Okay. Y inverse is actually same as Y. So what is Y, X, Y here? So what is Y, X, Y? What is Y, X, Y? Okay, I copy something wrong. No wonder I cannot see Y, X. Okay. So here become what? Become X squared Y, Y. Okay. X squared Y, Y is what? It's X squared. Because Y squared is identity. Okay. And then what's the next? Y, X, X, X inverse, and then Y inverse. Okay. So you get Y, X, Y inverse again. So you are X squared again. Okay. How about the next one? Y, X squared, X squared to the minus 2 Y inverse. So what is this? This is again Y, X, Y inverse, which is X squared. Okay, so meaning what? You conjugate x with the product of x, you still get x. But if you have a product of y and x, you get x squared. Okay. Sorry? Why does the y inverse equal to y? So you need to check what's the relation on y. Y is an order 2 element. Remember last time we showed that whenever your element is order 2, you are the inverse of yourself, right? Because if y equals to identity, what happened? You can multiply y on both sides. Okay, so if we don't want to multiply y on both sides, we can apply y inverse on both sides, which you get y equals to y inverse. Okay, if you are order 2, then you are the inverse of yourself. Because what? Y equals to identity, meaning left multiply by y, right multiply by y, you get identity. This is the definition of inverse. Okay or not? You can use definition, you can use algebra. Okay. Any question, other question? Okay, so let's take a break until 10:17. We'll come back with rings. Not exactly. You'll see a lot of theory of ring repeated groups. Hey, can someone call what's happening to Mingxiu or not? Uh,
现在这个对，这个对，怎么？可是这个 S 你要知道，这个是一个 element of S，这两个 S 不一样，这是小 S 跟大 S。为什么？非常完全是？好像完全，我 group action 一开始没记得。什么 group action？我从 group action 从哪里就不懂了 ？group action 什么 action？哦，group action，哦，OK，呀。然后你下面这个很乱哈，那个这样我要 quantify 那个 X 先。该写的。一样的。一样的没？我只是加了一个 quantifier 不了。对啊。就是当我说一个小 s 的 OS 等于 S 的时候，这样这个肯定是。这就是 there is 啊。但是你刚才你是写的，这为什么会？哪里？我在讲 there is，我那有讲 there is。其实我没有 quantify 它，其实 there is 跟 for all 这两个是 equivalent。是 different 而已。我知道，但是 for 这个题目是 equivalent，因为 OS 是一个 equivalent relation 来的。你只要有一个了，全部都是啊。但是这个是 special 啦 ，but 所以我要，这个非常好的问题。就是说，他们两个是 equivalent。等一下啊，等一下。你的partition 我没有印象，你在哪里讲到？讲 equivalent class 的 partition，object partition。在介绍 object 的时候吧，在介绍 object 的时候。object partition。放 equivalent classes 一样。啊，对啊，你只要一想到 equivalent class 就要 partition 就要 equivalent。非常好。对哦，这两句话是一样的，看得出。看不出，完全看不出。这跟 orbit 有关系，跟 transitive 这个字都没有关系，就跟 orbit 有关系吧。 如果你有一个 orbit 是你整个 S 的话，意思说什么？全部人都活在同一个 orbit。对啊。但你去看全部人的 orbit 的时候，那肯定也是 S 哦，因为全部人都活在里面。那同一个 orbit 就是全部人的 orbit。
这只是 subset 啦，
没有 subset 呢？什么叫做 subset？好吧，写这个出来吧。我觉得这个是非常好的问题。
现在
啊，
对的吗？
set one element 对。我看一下，我写一下。
再问了，
会
再问了，或者是你问。
嗯。OK 啊，大家讨论一下，可以吗？有人 call 明秀吗？
哦，
Hello, pending. Okay, let's take the attendance. Venus, hi Venus. 乐天, Wizard. Wizard, have you submitted your assignment yet already? This morning I haven't seen it. This morning, okay. 上儿, Yanker, Yanker, you still have problem with your assignment or not? You haven't submitted. Sorry? This morning you submitted, okay. Zari, okay. Raylan, yeah. Siyu, Helen. Ginseng, Xunling, yeah. Aaron, Jingbo, Hua Ying, Hishon, okay. Inqi, yep. He Yi, yeah. Shi Yan, yeah. Jia Ye, okay. Li Kai, Yuan Jia, how's your eyes? You get medication or not? You get it? Still not good? Cannot open? Hard to open? Better? Huh? Okay, okay. 文硕 eating, yeah. 玉维 yeah. 燕博 很夜 okay. 林晶 not here. 董洁 yeah. 周 yes. 丁宇 okay. 柳晴 曾诚 yeah. 硕宁 武力 子倩 德轩 莹莹 yeah. Grace okay. 再见 嘉文 Sue Michelle Ryan Ellie not here. 雪梅 not here. 子源 yeah. 嗯 if you guys see Ming Xiu, please encourage him more, okay? Please encourage him more. Yeah, please encourage him more because human like to close themselves, you know. So you need to encourage them more. Okay, so they can come up better. Sorry? Sorry? Yes, you also need. So we need encourage from each other. Okay or not? Nobody encourage you. Oh, so sad. Please encourage question also. Okay, yeah. Did I encourage you or not? Of course. Okay, cannot be too greedy. Okay, yeah. Okay. So got someone encourage you, okay? Yeah, so it's very important to have friends so that you can encourage each other. Otherwise, you'll be alone, getting more alone. And then you will break the social norm. What do you mean by break the social norm? So why do we have norm in the social? Because you want to get accepted by the others. And that's why you follow the norms. Okay, this become how to say a practice. Okay, so you follow the social norm. For example, why we have moral values? Okay, why we have moral? Because this is the what?
Why for moral?
Why to have moral? Moral is important for your study. You know, if your moral is not good, then probably your study is also not good. Okay. Yeah. So yeah. So moral is the thing that you use to like how to say it's the it's the it's the bad. It's the bad. No, it's not the bad. Bad is 赌注. Is the what? Is the
betting sheet.
no, I don't want that. That should be a proper word. Is the not the cost. Cost is simple. Is the cost. I don't want that. Change another word.
Bargaining chip.
Oh, bargaining. Okay, bargaining. Bargaining what? Bargaining tools, not tools. Bargaining. Bargaining. What? Is the bargaining?
So 为什么突然 moral？
We'll talk about this again, huh?
为什么会突然讲到 moral？
Because I don't know for you, at least for me, sorry. I mean, at least for me, sometimes when I start on one question, right? Okay, I mean one problem, will somehow get the answer by changing my personal view on something else. When I see something differently, somehow I solve this seemingly unrelated mathematical problem. You know, why sometimes you get stuck? Why you always get stuck? Okay, you need to think about the process of stuck and unstuck. Then you'll know what's wrong with you. You know, when you start with one problem, why suddenly I know how to do again. Okay, I start again. Why I know again? So this process of stuck and unstuck is the place where you change your personality. You get what I mean? This is the place you see what's wrong with you. That's why I don't want to give you question like just changing number because you don't know what you are doing. If I give you different number, different question, different concept need to be used. Why I don't understand that concept at first, and then why I can accept the concept already. So the process between stuck and unstuck is very important. It's not just mark, you know. It's not just how many marks you get. It's the process of stuck and unstuck. This is where you grow. This is where you learn. Okay or not? Stuck is not a big problem, but you need to learn why you are stuck. Okay. Okay. So Jingbo point out this seemingly contradicting definition here. So somehow I use this two definition here. So you have do few of my assignment, right? I like to show like equivalent definition or equivalent statement, right? So you see, this two definition here, transitive. One of them is for all. One of them is that exists, right? So a group action is transitive if there exists a orbit or S equals to S. So here the S, little s here is an element in X, okay? So this is a small s, S in X. The bottom here is for every orbit or S. If you check all the orbit or X equals it, that all of them are equal to the set itself. Okay, I claim that these two are equivalent. Okay, so why is this equivalent? So to show that these two are equivalent, there's nothing to do with transitive. Transitive is just an adjective. Okay, so you need to check why there's this orbit or S equal to X if and only if for O or X equal to X. So this is something to do with what? Orbit. Okay, this is something to do with orbit. So what's the property of orbit? Orbit is what? This is something that you need to know to show this. What is orbit? Orbit, you need to know that it forms an equivalent classes. Orbit partition the group set, the set S. Okay, so this is the thing that you need to know. And then you should ask why this form of equivalent classes. Then you need to check why this form of equivalent classes. Okay, you need to check that it satisfies what? What is equivalent classes? It is from an equivalence relation. Okay, you need to check that it satisfies some equivalence relation. What is the equivalence relation? It is a relation that is reflexive, symmetric, and transitive. Okay, and then there's a theorem says that equivalence classes partition your set. Okay, so from the first one, if there exists an orbit or S equals to X means what? That's on your set S is partitioned by only one orbit. So meaning what? You can reach every element in your set through S. This means what? If you look at the orbit of every element in your set, the orbit is the same orbit or S. Okay, because everyone else is living in the same orbit. Okay, if you can read S to everything else, right? So the idea is be like this. So you got S here, and let's say you got, let's say OS1, say OS1 equals to S. Okay, and then I can reach from X1 to X2 to X3 to X4 if my X is equals to X1, X2, X3, and X4. Okay, then what? Then, meaning if I take OS3, OS2, OS4, I can reach to all the other elements through this S1. Okay, so this implies what? OX2 equals to OX3 equals to OX4 equals to OX1. Does it make sense or not? Question. If I have a path from S1 to S3, can I make a path backward or not? So say X1 equals to G S3. Can I go from S3 to S1? How do I go from S3 to S1? By adding on a group element. Implies that X3 equals to G inverse of X1. Okay? Yeah. Okay or not? So this path is actually reversible. Okay. So once I have a way to reach everyone, then I can go from every elements and then come back to the rest. Does it make sense? So this path is actually, this group action is reversible. This is actually the permutation, because permutation is bijective. In particular, it is invertible. The inverse exists. Okay or not? Does it make sense? So if my group action is transitive, okay, there's only one orbit equals to x, then meaning everyone else has the same orbit. Have to have the same orbit. Okay. Because you can see that once I have a path from one set element to the other, I can go from the other element to one another. Okay. Because my group action is invertible. Okay, well, I can go forward, I can come back and go to the other place. Sense? If it confuses you again, you should write down the whole argument now. Okay, try to write down the whole argument, the full argument. Okay. Any question? Okay. Okay. Maybe I will write down the full argument, then you can check. Okay. Can we go to ring? Let's go to rings. Because I cannot find rings. Just the easy answer. I try to find rings in my sticker, but there's no ring. So I find the closest one diamond. Okay, yeah. Maybe I like karat more. Diamond, the unit for diamond is karat. Yeah. Right, before that, before we go into the ring, if you notice in your textbook, if you do pre-reads, you will see some German, I think German phrase there. And I try and Google it. What it says is, please forget everything you learned in school because you haven't learned it. So we will relearn the number system like integer, real, complex, in the context of rings. Okay, in the context of rings. Okay. Please forget everything you learned in school because you haven't learned it. After you learn, you can forget. Okay, so what's ring? Okay, it's a set or it's a map? Okay, it's a set. Okay, so this ring, what's the difference between groups? Groups only have one of law of composition, but rings we have two. So the typical example of ring you should remember is the integer. Okay, must remember this. Integer is a ring. Okay, integer is a ring. This is a basic ring we have. So I will explain to you why integer is a ring, but keep in mind when I talk about ring, integer should straight away pop up in your mind. Okay, when we talk about rings, you should think of what should you think of? Integer. Okay, so later we will argue why integer is a ring. So let's define what's a ring. So it's a set. Okay, set with two laws of composition. Okay, now we set two of them. One of them we call addition. The other one we call multiplication. Okay, there are two of them. One we call addition, one we call multiplication. So is it true for integer or not? Can you add? Can you multiply? Okay, we can do both these things. So one, yeah. After I introduce this ring, then we will briefly talk about what's the relation between vector space. So we have two operations here. One is addition, one is multiplication. So how do we add? How do we multiply? Okay, so these axiom we need to check. So with respect to the law of composition of plus, okay, we want this R to be an abelian group. Okay, meaning what? Meaning when I add, the addition is commutative right? A billion. And then what does it need to be satisfied as a group? Every element must be invertible. Okay, identity is in there. And then what else? That's all. Associative. Okay, addition is associative. How to add three things together? No matter you add the two first or the last two first is the same. Okay. Commutative. Yeah, commutative. Yeah, group. Yeah, a billion. So you need to be commutative. Okay, so let's write it down here. So this means what? Associative. Okay. Identity as this. Inverses as this. And then commutative. Okay, it's an abelian group. And we will denote this as R plus. Okay. And then the identity here, automatically we will call it 0. Okay. If something is addition, the operation is addition, we will call the identity 0. Okay. Call it 0. It's like the 0 in the integer. Okay. It's like what 0 does in the integer. And then how about multiplicative? Multiplication here, we are a bit relaxed. We're a bit relaxed here. Okay, what do I mean by relaxed? We only require commutative and associative. Okay, and then has an identity. An identity denoted by 1. Okay, we'll call it 1. So Z here, what's the problem with the multiplication in Z? There's no inverse because there's no fraction there. Okay, so we don't require you to have a multiplicative inverse, okay, for every element in ring. Okay, so in ring, it might not be invertible in the sense of multiplication. Does it make sense? So you think of Z. Is 2 invertible or not? Here we take it to be commutative. Yeah. For the R13 one, we take it to be commutative. Yeah. Actually, this is what we call a commutative ring. This is what we are interested in. Yeah. So you can throw away commutative, then we will see non-commutative ring, but the ring here we consider commutative. But this is the definition we will use in this course here. Okay. Actually, this is about commutative ring, but this is only what we care in this course. Okay, no? Yeah. How about closure? What's closure? Closure. Yeah, closure. So closure is included in the law of composition. When we talk about law of composition, right, it's G cross G to G. So it's like R cross R to R. So it's included already when we talk about law of composition. Okay. Yeah. And then C, you need to tell me how this addition and multiplication interact with each other. Okay, how they interact with each other. This is what the distributive law will give you. Okay, so for all ABC in my ring, A plus B times C, okay, is equals to A times C plus B times C. This is the usual opening up bracket that you know from your high school. Okay, it's the same. This is what we call the distributive law. You can show. Yeah, now this is left and yeah, you can show it. Yeah. Yeah, show it from the commutative point. Yeah, so Siyu asked about how about what if I multiply C on A plus B? How about this? Okay, but our multiplication is commutative. Okay, so we can write it back to A plus B times C. Okay, no? Yeah. Any other question? Any other question? So have you checked that whether Z satisfies this property or not? is 2 times 3 equals to 3 times 2. Okay, can I distribute? Is multiplication there associative? Okay, is the multiplicative identity 1? Is the additive identity 0? Okay, in Z. Okay, so you need to check all these property here. Does it make sense? Okay. 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 So similarly, if you have a group, you have a subgroup. So in ring, we also have a subring. Yeah, so what's a subring? So a subring of a ring is a subset that is closed under the operations of addition, subtraction, and multiplication. And that contains the element 1. Okay, so basically it's just a subset that satisfy all the ring property. Okay. Actually, I don't like to put the subtraction here. Okay, because subtraction is just something coming from the inverse. Yeah. Okay. So basically, it's a closed subset that satisfy ring axiom. So what are the example of ring? Okay. Some of them you keep, yeah. Right. Yeah, if I have subtraction, then we don't need to put 0. If don't have, then need to put 0. Yeah, so how to say? So if I throw away subtraction, then 0 should put in. If I don't throw away subtraction, then 0 will come out. Addition you can get using inverse. Yeah. So one can also be produced using inverse. Oh, one cannot be produced. Okay, true, correct. Yeah, correct. So yeah, correct. You are correct. So how about 0? So question, a very good question. Oh, good question already. So so question here. Does subring contain 0? Okay, the subring contains 0. From definition, for all as let me see. Let me see. Yeah. So okay. So if I remove subtraction, then I need to include 0. Okay, because I don't know whether it is invertible or not. But if I include subtraction, depend on what this subtraction means, right? Yeah, depend on this what this subtraction mean, right? It doesn't say that every element should have inverse. Let me think. So what does this subtraction mean? Yeah. Okay, so let's throw away this subtraction and then we say that 0 must be in there. Okay, yeah. If I have subtraction, meaning I can subtract everything in my, I have subtraction for every element, right? So if x minus x, then maybe I don't know what is x minus y, but I definitely know what is x minus x, which is 0. Yeah. Okay. Yeah. Yeah. Question. Yeah. For multiplication, we have so is the multiplicative identity for integer is 1. Yeah, that's true. That's true. So that's why ring. So in ring, we don't require every element is equal. Yeah, for multiplicative one. Yeah, but for addition, everything must have inverse. You must have additive inverse in your ring, but not multiplicative inverse. This is the this is the point. But if we have multiplicative inverse for all of them, this is what we call the field. And later we will introduce field again. Okay. Yeah. Yeah. Okay or not? Okay. Yeah. Yes. So you need to talk about additive identity or multiplicative identity. Okay. Yeah. So you need to be more specific now, because I have two operations on ring. So you need to tell me what is the multiplicative identity, what is the additive identity. Right. Any more questions? Good, 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 very good. Okay, so example, what kind of ring you have seen before? So complex number, for example, real number, integer, right? Okay, and then actually integer modulo p, okay, also a ring. Okay, integer modulo p, you can add, you can also multiply. Okay. And why we look, I put p prime here, so p prime is what we call the fp. Okay. I think later we will talk about this, but I want to keep it like this first. I want to introduce notation. Actually, it means field. Yeah. Maybe we can talk about it later when we do field. But I want to call it a new name, FP. Okay. Give name, give name. Give name first. Okay. Or sometimes you will see a Gauss integer. Okay, for example, this set here, which is a plus bi, such that a, b are in z. Okay, so what is complex number? Complex number is just r, this square bracket I. Okay, yeah. So let's call them, call these, all of these, call them r. Okay, let's call them r. Okay, these are the ring. So we can do more things. We can consider polynomial ring. And let's do a polynomial ring. So still remember what a polynomial ring is? This is R. This square bracket here, we will call it adjoint. Okay, let's call it adjoint. Later, we will define this more specifically. Let's call it adjoint. Otherwise, I keep saying R square bracket X. Right. So let's say R adjoint X. Okay. So I'll put here R adjoint X. Okay. So what is this? So these are all the linear combination of the monomial X to the I. Okay. With the coefficient in the respective ring. Okay, so this ring you can imagine these are complex, real, or integer modulo p, or Gauss integer, anything you can imagine. Any ring adjoined with x. Okay. So for example, let's take an example. What is zx? So what are in zx? For example, what? 2 plus x is in there. Right? Okay. So you can see that all the coefficient live in Z. Everyone see? Okay. So for example, what? 0.5 x squared is not in here, right? Because 0.5 is not in Z. Okay. Does it make sense? Okay, and then this power here, right? So something to take note here. The power here is finite. Okay, here is finite. It's not like power series. Right? Here is finite. You stop at certain power of x. Okay, for example, what? For example, 3x plus 6x to the 100 is in there as well. Okay, it's finite linear combination. Make sense? Okay, so this is called a polynomial ring over R. Okay. What else? So we can extend this example, right? We can extend this example. We can consider formal power series, right? This is what we learned in calculus 2, right? Okay, formal power series. This is called the R double adjoint, okay, X. Okay, so here we are allowed to take the power to infinity. Okay, we are allowed to take power of infinity. Okay, so we can add power series together. We can multiply two power series together. Okay, makes sense. Okay. So in polynomial ring, okay, there's one thing that's not good about this polynomial ring is we cannot find the inverse of the polynomial ring. Okay, so how about we add the inverse in? Okay, let's add the inverse into our polynomial ring. This is what we call the rational polynomial. Okay, we add inverse to the we add inverse to the polynomial ring. Okay, so this set is P over Q such that PQ is in Rx polynomial ring and PQ have no common factors. Okay, so here what do? We are like invert everything except 0. We don't invert 0 in Rx except the 0 polynomial. Except CERPT, the 0 polynomial. Okay. So for example, here I can find S1 over X. Right? I can find 1 over X here. And 1 over X squared. Okay. So this is a bit like the construction of rational number. So that's why we call rational polynomial. Okay, no? So this is a round bracket. Okay, the above is a square bracket. Okay, so if I put one square bracket, it is finite linear combination. But if I put double square bracket, this is a infinite linear combination power series. And then if I put square, if I put round bracket, this become a you have multiplicative inverse other than 0. Okay or not? Okay. And what else we can do? And then I'll keep continue. So we can continue with something what we call the Lorentz polynomial. Okay. So what's the Lorentz polynomial means? So it means that I can extend. Okay, I can extend my polynomial in the negative direction. Okay, so I include the finite linear combination from negative degree. Okay, let's call the power of the x, the degree of x, to positive. Okay, and vice versa. So we include negative x inverse. Okay, And then because Foremost power series just continue one direction, right? From constant to positive power of x until infinity. What if we continue to the negative infinity? So we include both lines, negative infinity to infinity. Okay, this is what we call the Lorentz series. And the Lorentz series will be used in a complex analysis. So this is a double x notation. This is what we call Lorentz series. Okay, and your task is try and show that all these things is a ring. Okay, show that all these things is a ring. Yeah. Yeah. Do you need to care about convergence? You need to care about convergence. Technically yes. Technically yes, but the problem is, can you come up with addition or not? Can you come up with multiplication first or not? Okay. What's the multiplicative identity? What's the multiplicative identity? Okay. Yeah. Actually, showing all these are quite similar, but showing convergence may be a bit quite tricky. But the addition, multiplication should be obvious. Yeah. It's similar to the polynomial ring case. Convergence is a bit tricky, so you need to have some convergence in this topic. Yeah. Mm-hmm. Mm-hmm. Yeah, you need. But for finite linear combination should be just finite. But infinite then a bit tricky. Yeah, for infinite it's a bit tricky. Okay or not? Yeah. So this assignment will be about until showing something is a ring. So you should be able to start your assignment already. So please don't wait until last day. Please don't wait until last day. Please start now. Start now. Okay. We already cover everything you need in your assignment. Please start now. Don't leave up until last day. Okay. Okay. If not, leave all the questions to next lecture. We will address them.